So in this video I'm going to review the physics benchmark test and go through the various sections so we can look at improving your answers. Okay, so the first section we looked at some estimation. So with each of the sections, essentially the questions are leveled. So the first one should be fairly straightforward, the second one should be a little bit more challenging, and then the third one sort of like the most challenging. But we've only covered a few topics, so we're not into the most challenging content of the physics course yet. So let's get started. So, estimate the external surface area of your physics folder. So, most folders are essentially on the front side and back side. They're going to be about 30 by 20 centimeters. So that the area of those is going to be 0.3 times by 0.2, and when we do that calculation, essentially put those numbers in meters, we get 0.06 meters squared. And then there's the binding section, so 30 centimeters times by about, I'd say about, I don't know, 10 centimeters. So we're sticking nice and rough. The area is going to be 0.3 times 0.1, so 0.03 meters squared. So your total area is going to be 2 times 0.6, because there's a back and a front, so 0.06 times by 2. And then you're going to add on 0.03, and we're just going to end up with 0.15 meters squared. So you might not have got exactly that, but you should have used a similar kind of method and got a similar type answer. So estimate the volume of your head. So I'm going to approximate it as a sphere. And since we're doing approximation or estimation, we can say pi and 3 roughly cancel out. So you'd get a rough approximation like this. If you kept the 3 in the pi, that's absolutely fine, but it's an unnecessary level of detail. So what do I reckon is the radius of my head? Well, if I take rough measurements, I would say its diameter is about 20, so its radius is going to be about 10 centimeters. So it's going to be 4 times 0.1 cubed. So 0.1 cubed is 10 to the minus 3, so it's going to be 4 times by 10 to the minus 3 meters cubed is your answer there. And sorry, I should box all these so you get the answers. Okay, so you might have decided to model it as a box and do the volume that way. Also absolutely fine, there's a perfectly reasonable way of doing it. This is just my chosen method. Estimate the grains of sand that can fit in a typical swimming pool. So I am going to model grains of sand, that's the best I can do on this, as 1 millimeter cubed, which is going to be 1 times 10 to the minus 3 cubed, which is 1 times 10 to the minus 9 meters cubed. So that's the volume of a grain of sand. You might have modelled it as a sphere, that's fine too. A swimming pool is usually about 25 meters by 15 meters, and then let's say on average it's about 2 meters in depth across the whole length of the pool. So that's going to give you a volume of 750 meters cubed. So to get the number of grains, we're just going to take the 750, divide it by the volume of 1, and so let's do that. So divide by 1 times 10 to the power of minus 9, which gives us 7.5 times 10 to the 11 grains. Okay, so those are the 3 estimation questions. They should be fairly straightforward to do. Things to bear in mind, so like here, don't get too precise with it. Cancel things that are like the same or very similar. Approximate things as nice shapes, so spheres, cubes, that kind of thing. And don't get too hung up on the estimations that you're making. We're just trying to get approximation, so pick nice values to use. Okay, so that's that. So let's move on to some dimensional analysis and base units. So one of the things you need to know in the course is the different base units, and then you also need to be able to turn SI units into them. So let's have a look. So first, let's start off with some SI units. So SI unit of mass, hopefully you should know, is the kilogram. Don't get tempted to write grams. If you do chemistry, they'll tell you all about grams and how great they are. It's kilograms are the SI unit, and the SI unit of distance is meters there. So those are your units. So we're going to use F equals kx, which you may or may not know is Hooke's law. So we want to use it to determine the base units of k. So the first thing we do is we rearrange it to make k the subject, like this. And then, so we're going to substitute in the units. So force is a Newton, and then x is a meter. And using Newton's second law, a Newton is kilogram meters s to the minus 2. Divided by meters gives you kilograms s to the minus 2, because your 2 meters top and bottom cancelled out. And that gives you your base unit of spring constant there. So that's the method I was looking for. So there's 2 marks here. So the first was getting to this stage, so rearranging and subbing in the SI units, then moving into base units and simplifying for the second. Okay, so then we've got Newton's law of gravitation. So we're trying to determine the base units of G. So as before, you rearrange into make G the subject. Let's put the SI units in first. So we get in like that. Then we're just going to do kilogram s minus 2 dot meters squared over kilograms squared. So we can cancel that and the power. So we'd end up with meters cubed s to the minus 2 kg to the minus 1. And that would be the base units of G, which is the universal gravitational constant. So the same process here. This stage is worth 1 of the marks, so rearranging and subbing in. And then for cancelling and getting the correct answer, again, the second mark there. Okay, so that's that section completed. Let's move on to some vectors and results. Okay, so before we finish, it's gone off screen. That should be an 84 newtons there. Okay, so we've got a displacement vector. So I've already written the wrong thing in there. It's a displacement, so it's in meters. Resolve the displacement into horizontal and vertical components using trigonometry. So when we're resolving into components, what we're doing is we're forming our right-angled triangle like this. So the displacement is the hypotenuse, and then we've got, essentially we're splitting it up into those 2 components with the angle in there. So using trigonometry, let's call that one x and that one y. The horizontal displacement x is going to be 84, and that's going to be multiplied by cosine of 30, because it's the side that's adjacent to the angle. Cosine of 30 is root 3 over 2, so that's going to be 42 root 3. In physics, we don't leave stuff as fractions, so hang on, cos 30 times by 84, so it's 42 root 3, which is 73 meters. So that's x, and then y is opposite to the angle, so it's going to be 84 sine 30, which is going to be, sine 30 is a half, so it's just going to be 42 meters there. So those are your 2 components. So hopefully quite straightforward. Then we're going to look at this one, which is a question taken from a past exam a few years ago. So we've got a glider being launched with various forces acting on it, and the diagram shows that, and then it essentially wants us to work out what the magnitude of the resultant force acting on the glider is. So the first thing we do is we cancel out parallel forces. So let's call this the x direction, this is the y. So the resultant force in the x direction is going to be 7200 minus 1200, because we can see this force is acting to the right, this force is acting to the left, so they cancel each other out, ends up, bam, 6,000 newtons. The resultant component in the y direction is going to be the upward force, so 7,500 minus 6,500, because essentially, just as before, this one's up, which is the positive direction, this one's down, which is the negative direction. And again, 1,000 newtons. So to get the resultant, we're essentially using some Pythagoras. So what we're going to do is 6,000 squared plus 1,000 squared square root, and we'll get 6.1 times 10 to the 3 newtons as your resultant force. So where were the marks for this? There was essentially a mark for getting the x component, a mark for calculating the y component, and another one for getting the correct answer. So the unrounded answer is like 6,082.7 blah blah blah, but we're going to round that to two significant figures here and write it in standard form. Okay, so calculate the angle between this resultant force and the horizontal. So let's draw a diagram of what these two forces look like. So we've got a resultant is this one. This was Ry and this is Rx, because this is in the x direction. So it wants the angle to the horizontal, so it wants that one in there. So we know that we take the tan of the angle, it's going to be opposite, so Ry over Rx. So the inverse tan y was 1,000, x was 6,000. So let's do that. 1,000 divided by 6,000. Inverse tan of answer gives you 9.5 degrees. And that concludes the benchmark review. I hope you found that useful, and we'll move on.